All right, so today I'm going to talk about how we can learn statistical models that can maintain a uniform level of performance even across minority subpopulations. Can everyone hear me okay in the back? All right, so this talk is going to be based on a bunch of joint works with my advisors, John Lucci and Peter Glynn. All right, well, I guess my remote is kind of flaky, so I'll just stick to the... All right, so powered by recent advances in machine learning, a lot of these algorithms are now beginning to be applied in a number of decision-making scenarios, including high-stakes domains like diagnosing diseases, prescribing hiring decisions, and evaluating loan applications. And in order for these statistical models to maintain a reliable level of performance when they're deployed, they need to work uniformly well on the heterogeneous set of populations that they may encounter during operation. However, the machine learning community is currently having this collective freakout because we're slowly realizing that these standard models that were optimized to do well on average, they actually perform quite poorly on certain subpopulations, such as underrepresented demographic groups and tail inputs. So most recently, I think it was a few months ago, there was an article about how Amazon had scrapped its plans to automate parts of its hiring process because they realized that the model that they were developing was discriminating against women and rejecting candidates based on keywords like women's college in their CVs. And it's probably not the case that Amazon came up with some magical sexist AI, but that the data sets and the learning procedures that they used were susceptible to the inherent bias in this domain, the gender gap in the tech industry. And it's not just Amazon. Algorithms are now ranking job candidates at LinkedIn. They're also matching candidates to divisions at Goldman Sachs. And a lot of other companies are following suit. Now, perhaps more concretely, to see the shortcomings of a typical statistical model, here I have a medical example. So in this setting, we want to come up with a personalized drug dosage for warfarin, which is the most commonly used blood thinner in the world. So here, given demographic and genetic information about a patient, we want to predict the patient's therapeutic dosage of warfarin. And a few years back, a group of researchers, doctors, came up with a dosing algorithm based on a linear regression model. And they amassed a fairly big supervised data set for this task. And they showed that this dosing algorithm, based on the simple linear regression model, worked best out of a number of more complicated statistical approaches. So here I took this dosing algorithm and I applied it to a clean set of out-of-sample patients. And then I computed the prediction errors incurred on their therapeutic dosages of warfarin. And I sorted these values, and that's the red line that you see over here. And here I'm also plotting the average case error. And we see that this dosing algorithm, it performs really well on average. The average case prediction error is really low, the black line. But then if you look at this group of people, then it completely mispredicts their therapeutic dosage of warfarin. And in other words, the tail performance of this model is orders of magnitude worse than its average case performance. And this is quite scary considering the fact that another popular use for warfarin is rat poison. So apparently it's very effective at killing rats because it keeps their blood from clotting. So you really don't want to be in this group of people. And this underperformance, this phenomenon of poor tail performance, it's been observed in a number of different applications of statistics and machine learning. And this unreliability is oftentimes accentuated by the a number of challenges that we face throughout many different applications of machine learning. So the first of these challenges is that the data that we observe are oftentimes long-tailed. And this is true throughout applications in social and natural sciences, as well as internet applications. So for example, at Google, a constant fraction of queries are new each day. And you can see this concretely on this plot of query frequencies based on a public data set released by Microsoft Bing. So in the search engine example, common queries, like, say, the Beatles, they're quite easy to answer because a lot of people search for this keyword every day. But then if you search for Hongseok Namkoong, no one knows who that is. And this is really where you have to learn and extrapolate and be smart. And according to a Bing engineer, this is where Bing suffers compared to Google. So it's really these tail inputs that determine the quality of service in this setting. And this is oftentimes true in a number of different applications. Now, another core challenge that we currently face is that the data sets that we use to train these models with, they're oftentimes deeply biased, and they severely lack diversity. So for example, in medicine, it's well known that the clinical trials for new drugs are heavily centered around Caucasian groups. So from 1993 to 2013, 98% of all studies on respiratory diseases did not report any inclusion of minority subjects. And this is despite the fact that racial minorities like African Americans are more likely to suffer from these diseases. And in computer vision, the supermajority of the images that we use to train deep networks with, they're collected in either the United States or Western Europe, showing a severe lack of geodiversity. And this underrepresentation bias, it's been observed in a number of different applications, some of which are listed here. So this bias is really something that should first be addressed at the beginning of the pipeline at the data collection phase. And we as a community need to think hard about the best practices that can potentially mitigate some of these issues. But at the same time, this bias is propagated and heavily exacerbated by the types of learning procedures that we use. So despite the long tail data and these underrepresentation biases, the standard machine learning paradigm, it trains models to only do well on average. And this oftentimes produces statistical models that have very poor tail subpopulation performance, as you saw in the warfarin dosing example. So before I go into the shortcomings of the standard paradigm, let me first briefly set up a few notations so that I can use it throughout the talk. So today I'm going to use L to denote the loss or the objective that I want to optimize. And I'm going to use theta to denote the parameters of the statistical model or the decision that I want to make from the data. And I'm going to use Z to denote the random data that you observed based on the data generating distribution, P observation. So given this notation, the standard machine learning paradigm, or the stochastic optimization setup, is to find decisions or statistical models data that minimizes this expected loss under the data generating distribution, P observation. So this generic loss minimization framework, it encompasses a lot of the supervised learning scenarios. So for example, linear regression was what we used in the warfarin dosing example. And it also includes support vector machines, logistic regressions, and a number of more complicated losses in classification, as well as more complicated models like deep nets. And of course, in OR, this setup has also been extensively studied with many applications ranging from news vendor type problems in inventory management to portfolio optimization in finance. Now, to concretely see the shortcomings of this standard average case approach, let's take a look at this example. So here are labeled faces. Is a gold standard data set for facial recognition. And it's 80% male, and it's 80% white. And as a result, these commercial gender classifiers that's been trained on these types of biased data, they show widely disparate performance across different demographic groups. So at the risk of using a binary reduced notion of gender, if you look at the performances of these classifiers in this table, and then you can see that they all perform pretty well on these green demographic groups, and almost perfectly for pale male faces. But then for females with darker skin tones, it do really poorly on. And this gap in performance can be as large as 30 to 35%. And here it's also worth noting that the disadvantaged subpopulation was given by a combination of two demographic variables, your skin tone and gender. And while this particular study only looked at two different variables, it's usually true that the most disadvantaged subpopulations are given by a combination of multiple demographic characteristics. And this is what makes this problem particularly challenging, because even identifying these disadvantaged subpopulations can be quite challenging and non-trivial without actually having trained and deployed your model.
May I ask a question?
Of course.
So how do you think of this? Is this because this is a problem of data collection a la measure P? Or is this a matter of using a different performance measure as opposed to expectation, use some sort of a tail?
Good. So, good. I'm saying that it's both. So it's oftentimes exacerbated by the fact that you have these biased representations of certain demographic groups. But even when you have perfectly balanced scenarios, as we'll see in one of the experiments, there's actually these fundamentally more difficult subpopulations that sort of naturally arise. And they usually form this tail portion. So even in these balanced scenarios where you are careful about data collection, this becomes an issue. But even if you have actually biased data sets, then it's even worse. Thank you. Okay, so before I go into the details of my approach, I'm going to first lay out a simple natural idea and briefly explain why it falls short of what you'd actually want in practice. So you can think of maybe coming up with a set of predefined demographic groups that you're going to protect against. I'm going to denote this by G. And maybe you can train a separate model for each of these groups, or you can train one model to optimize performance on the worst of group. So this is a natural, simple idea. It has a few key limitations in practice, some of which I actually alluded to in the previous slide. So in a number of software applications and services, for example, speech recognition, it's usually the case that these demographic information is simply not available because it's not appropriate to collect them. So for example, Siri, Apple's voice assistant, doesn't know that I grew up in Korea, and as a result may have this minority accent that may affect its performances. And even when you have these demographic information, actually coming up with these protected demographic groups can be quite difficult a priori without actually having trained and deployed your model. And this is because these oftentimes these demographic variables, they comprise a continuous spectrum. So skin color, for example, was a continuous variable. And it's somewhat unclear how to come up with the thresholds to discretize and partition this spectrum into a discrete set. And as we saw in the previous example, the most disadvantaged subpopulations are usually determined in an intersectional fashion among multiple demographic characteristics, like your race, gender, age, income, and in medical scenarios, your genetic information as well. And once you start accounting for all of these intersections, you're going to soon end up with an exponential number of these protected demographic groups, rendering either of these approaches both statistically and computationally infeasible. So just to belabor the point that coming up with these disadvantaged subpopulations or protected demographic groups is a pretty non-trivial task. Here, let's go back to the warfarin dosing example again. So here I'm plotting the prediction error incurred on each racial group. And here we do see that blacks do suffer slightly higher prediction error than whites. But then if you look at the 90th percentile of the total losses, then you can see that there is about 10% of the population who suffer significantly higher losses, prediction error, than any of these individual racial groups. Now, in this particular setting, we can do a bit more digging and try to figure out, at least partially identify, who these group of disadvantaged subpopulations are. So if you look at, for example, patients who require a high dosage of warfarin, then Asians among that category are quite rare, about 1% of the total population. And as a result, they suffer really high prediction error on par with something like the 93rd quantile of the total losses. But to identify this very particular group a priori without actually having trained and deployed your model is a pretty challenging task. So today I'm going to talk about a statistical procedure that can automatically identify these worst of subpopulations and train models to optimize performance on them. And by virtue of taking this worst case approach, we're going to be able to guarantee a uniform level of performance across all large enough subpopulations. And our procedure is going to be computationally efficient so that it can scale to these large modern applications of machine learning. And theoretically, I'm going to give a number of results that quantify what it means to optimize this worst case subpopulation performance. And in particular, I'm going to characterize the fundamental statistical price that you have to pay if you want to optimize these subpopulation performances.
So maybe this is taking a jump ahead a bit, right? Is there some assumption that there's some set of features that predict what the subpopulation is going to be, or does this work even if that subpopulation is effectively a random subset?
Good. So today I'm going to mostly focus on the latter setting where you fully have these joint shifts. So minority distributions defined with respect to whatever randomness that's in the system. We can generalize the procedures that I'm going to talk about today to specific settings where you want to hedge against maybe minority proportions with respect to race, gender, and income only. So that's actually going to be an extension of our works, which I'll be happy to go into detail offline if any of you are interested. Thank you. Okay. So the way I'm going to do this is by leveraging a rather classical idea and that many of you have probably seen before. So in operations research, economics, or finance, when we make decisions, we almost always try to be risk averse because we don't want our fulfillment centers running out of stock during the holidays, and we want our pension funds invested in a smart way so that they perform reliably even during a financial crisis. So I'm going to argue that being risk averse can be a very useful thing to do in large-scale machine learning scenarios as well. So to illustrate this, here I have two different statistical models, theta 1 and theta 2. And I'm plotting the PDFs of the losses or the prediction errors suffered under each of these models. So if you look at this black model, theta 2, then you can see that it has a really low expected loss. So if that's what you cared about, average case performance, then that's a really good model. But then if you look at the tails of this black distribution, then you can see that there's a significant proportion of the population who suffer really high losses under this model. The model theta 2, the theta 1, excuse me, the red model on the other hand, it has a slightly higher expected loss, but its losses are quite concentrated around its mean. So if you deploy the model theta 1, you sort of expect that it'll perform reliably throughout the whole population. And this is the key idea that I'm going to leverage throughout the talk today.
How do you get that curve in the first place if you don't know the data?
Oh, so this is the population distribution. So here I'm just explaining the idea. All of my procedures will be in the finite sample version, which only depends on the finite number of samples that you observe. Thank you. So here I'm saying maybe the population version itself that you should consider should be different than the simple average case model because your data sampling procedure may be biased for some reason.
Are you going to trade off average case performance for worst case?
Yes, good, yes. So this will be a key trade-off that emerges. And we're going to give a number of empirical settings where we show this. And so it's unclear when you're okay with this trade-off. But in high-stakes domains, like in the medical warfarin dosing example, you are completely fine with it because you really don't want to kill people, so you don't want to overly mess up dosages of people, so you're fine with trading off a few milligrams off of the average case. Thank you, that's a good point. All right, so in the rest of the talk, I'm going to build on this risk aversion idea and explicitly make a connection between these worst-case subpopulation performances and risk aversion. And I'm going to argue that this connection will allow us to build more reliable machine learning algorithms. And in particular, I'm going to propose a formulation that is computationally efficient to solve, and we're going to study its statistical aspects. So I'm going to quantify the extent to which we can optimize these worst-case subpopulation performances by only looking at a finite number of data points. And this is going to be our main theoretical result today. And then I'm going to, on a couple of real data sets, I'm going to empirically verify that our method can indeed identify these disadvantaged subpopulations and improve performance on them. And in the remaining time, I'm going to do a brief overview of my broader research agendas. So in general, I'm quite interested in the interplay between large-scale machine learning methods and decision-making problems that naturally arise out of operations research and other engineering domains. And I think there's a lot of really nice insights within OR that if they can be scaled up in the right way, can help us tackle some of these fundamental challenges that we currently face in machine learning and statistics. And the subpopulation story that I'm going to talk about today is, I think, is a particularly good instance of this. Okay, so to make concrete this connection between risk aversion and worst-case subpopulation performances, I'm going to start with the conditional value at risk, which is a very well-known tail risk measure. So CVAR is simply a tail average of some random variable, in this case the loss or the prediction error suffered under the current statistical model theta. So given some quantile level alpha, say 10%, CVAR takes the 90th percentile of this random variable here, and it just takes a tail average after this quantile level. Now, you can also represent it in its variational form, where eta here signifies the quantile level that you want to threshold at. Intuitively speaking, under the current statistical model, the set of people who are going to be the most disadvantaged are going to be people in this purple shaded region, because by definition, they're the people who suffer the highest losses. So if you consider a distribution that is centered on this tail portion, then you sort of anticipate that this will be the worst of subpopulation under the current statistical model theta. So I'm going to quantify this intuition. So in order to do that, I'm going to first define what I actually mean by a subpopulation. So today, in order to consider arbitrary demographic groups, I'm going to define subpopulations as a mixture component. So I'm going to say that a distribution Q0 is a subpopulation of P if there exists a demographic proportion A and some other distribution Q1, such that if you mix these two distributions together according to this demographic proportion, then you recover the underlying base distribution, the data generating distribution P. So pictorially here, Q0, this purple curve, is a subpopulation of P, the underlying data generating scheme, because if you mix in this purple curve with this gray curve, according to the demographic proportion A1 equal to 20%, then you exactly recover the underlying base distribution. So in this case, the demographic proportion was equal to 20%. So you can think of this purple curve as a minority subpopulation, and this gray curve as a majority subpopulation. And today I'm going to index these subpopulations by the demographic proportion A explicitly for reasons that will become clear in a couple of slides.
Target the current Warsaw subpopulation. What if your optimization creates some other Warsaw subpopulation?
Good, good, good. So this is actually the key aspect of this approach. So thank you. So the way we are defining these worst of subpopulations is adaptive in the sense that it depends on the current statistical model. So we're going to find a statistical model under which even the worst of people are reasonably well off. And this is why this natural trade-off emerges in certain scenarios, and sometimes it doesn't actually, for reasons I'll explain in a bit.
Are you able to characterize the family of subpopulations?
Good. So our worst case formulation will be over a family of subpopulations.
Are you able to characterize it?
What do you mean by characterize it?
If you vary all possible A's,
Mhm.
what is the class of subpopulations that is available that you can express in this form?
Good. In a sense, yes. Maybe I'll present the actual approach, and maybe you can, if that doesn't address your question, can you? Thank you. That's a good point. Okay, so here, depending on your demographic proportion A1, you can do this mixture in a number of different ways. So here's another way of doing it, where A2 is equal to 50%. Here's another, and here's another. Now, let's go back to the conditional value at risk, which again just was a tail average, this purple portion. So what this lemma shows is that the conditional value at risk at level alpha is in fact exactly equal to the worst case subpopulation loss, where the worst case is taken over subpopulations Q0s such that its demographic proportion is larger than the level alpha. So this is a worst case loss over all subpopulations larger than some level alpha. And this lemma quantifies the intuition that the worst of subpopulation is given by this tail subpopulation, and your loss, prediction error, suffered under the worst of subpopulation is given by this tail average, the conditional value at risk. Now I'm going to generalize this equivalence even further and make a connection between a more general notion of risk aversion. So in order to do that, instead of considering a fixed demographic proportion, I'm going to consider a random demographic proportion, or minority proportion. I'm going to use these terms interchangeably. And I'm going to denote this minority proportion as capital A. I'm just going to say that it follows some distribution P sub A. Now, in order to define a notion of worst case subpopulation performance over these random minority proportions, I'm going to consider a collection of subpopulations, given here, where they're indexed by the demographic proportion, and A ranges from 0 to 1. Now, I'm just going to view this collection conceptually as a conditional probability over these random data Z, given the random minority proportion, capital A. And I'm going to call this set of conditional probabilities as script P Z given A. So formally, this set is defined by the set of conditional probabilities, or collection of subpopulations, such that there exists another conditional probability. And if you, again, given any level of demographic proportion A, if you mix these two distributions together, you again recover exactly the underlying base distribution P. So this is the set that we just defined. Now I'm going to define a worst case formulation over these random minority proportions. So I'm going to do that by noting that if you take this collection of subpopulations Q0, and if you marginalize out the random minority proportion according to the marginal distribution PA, then you get a distribution over the random data Z. So this expected loss here, it quantifies the loss suffered under these collection of subpopulations according to this random minority distribution P sub A. And then I'm going to take a worst case over these collection of subpopulations, Q0s. And since I know very little about the random minority proportions themselves, I'm going to take another worst case over these probability distributions, P sub A, on the random minority proportion. So here, this set, script PA, is the worst case region over which I'm taking this distributionally robust formulation. And this expression here defines a general notion of a worst case subpopulation performance. Raghu, is that? And I'm going to make this concrete in a few slides.
You made the objective function clear.
Okay.
It's still not clear
how we characterize the good.
Characterization of the class.
Good. So empirically, we can simply just say, look, these are the set of worst off people. Of course, this worst case is now taken over infinite number of things. So it's essentially just a tail subpopulation. And our geology results does give an explicit way of identifying who these groups of people are because they're based on a certain threshold. At least the specific formulation that we're going to use will do this. Okay, so now given this worst case subpopulation performance, I'm going to now connect it to a more general notion of risk aversion. So to do that, I'm going to consider a risk measure, which is just a mapping from a random variable, the loss or the prediction error suffered under the current statistical model data, to a number that connotes a notion of risk. So, this mapping, this risk measure, is called coherent if it satisfies a bunch of axioms that represent what it means to have a sensible notion of risk preference, a sensible notion of risk aversion. So the first of these axioms is convexity, which just says that you have diminishing marginal returns, or its negated version because these are risks and not returns. And monotonicity, which just says you prefer smaller losses. And translation equivariance, which says if you have to suffer a constant amount of loss or prediction error, then your risk measure has to be worse off by that constant amount. And positive homogeneity, which says if you have to suffer 10 times as high losses, then your risk measure has to be worse off by 10 times. So these axioms quantify a sensible notion of risk aversion. And it was first proposed about 20 years ago by Artzner, and it's been extensively studied throughout operations research and finance. Now, let's connect this back to our worst case subpopulation performance. So this expression, I'm just going to denote it by script R sub script PA, where this was, again, the worst case region over which we're taking this conservative formulation. Now, what this lemma shows is that there's actually a one-to-one correspondence between these worst case subpopulation performances defined with a convex worst case region and these coherent risk measures. So being risk averse is actually equivalent to optimizing these worst case subpopulation performances. And this is a sense in which it might be very useful to be risk averse in statistical learning scenarios, especially given these long tail data and underrepresentation biases. Now, I'm going to actually make this practical and operationalize this. But before I do that, any questions so far? All right. So in practice, what we want is a tractable family of these worst case subpopulation performances so that they can smoothly interpolate between the standard machine learning paradigm, the average case scenario, and the other extreme, which is to consider the worst off individual in the total population and to optimize performance on that individual. And the way we're going to interpolate between these two regimes today is by modulating the size of this worst case region, the set script PA. So if this set is big, then this worst case subpopulation performance will become more conservative. And the specific way I'm going to do this is by positing a probabilistic lower bound on the random minority proportion, capital A. So this will generalize the fixed lower bound that we had in the conditional value at risk equivalence lemma. And in particular, this probabilistic lower bound will allow us to consider arbitrarily small minority groups defined in some probabilistic sense. And we'll see later in the experimental section how this actually empirically gives us a set of statistical models that are more robust to certain hyperparameter choices. So let's consider these random lower bounds U on our random minority proportion capital A. And since I don't know anything about these random lower bound, I'm just going to let it follow a non-informative distribution, the uniform distribution. And instead of lower bounding A, I'm going to upper bound 1 over A. So here I'm going to consider the moment of 1 over A, conditioned on the fact that U is indeed a random lower bound. So this conditional expectation depends on this random lower bound U. And now I'm going to take its qth order moment, and I'm going to say that this is bounded by some number 1 on alpha. And I'm going to consider the set of distributions PA on the random minority proportion that satisfies this constraint. So here 1 on alpha gives a notion of an upper bound on 1 over A. So alpha is again a notion of a lower bound on your minority proportion, capital A. So this is some set with some interpretation. But why is it actually practically nice? So that's what this next lemma says. So again, this is the set of probability distributions over these random minority distributions that we just defined, the worst case region. Now, if you consider the worst case subpopulation performance defined with this very particular worst case region that we just defined, I'm going to denote this by script R sub P alpha. Then this lemma shows that it has a really nice dual form that doesn't have these nasty soups over infinite dimensional spaces. And this dual form is highly reminiscent of the variational form for CVAR, the conditional value at risk. And in particular, it's exactly equal to the conditional value at risk when P is equal to 1. And as P grows, this formulation becomes more conservative. And this is, in fact, the higher order generalization of CVAR that was first proposed by Krochmal about 10 years ago. Now we're giving it a new interpretation from this worst case subpopulation lens. And so again, recall that Q was the conjugate of P. So as P grows, Q goes to 1. So this moment term, the Qth order moment, becomes smaller and smaller as Q goes to 1. And this set of distributions, the worst case region, becomes larger and larger, hence as P grows. So this is a sense in which this worst case subpopulation performance becomes more conservative. So given this very nice dual form, instead of optimizing for this average case performance, as in the standard machine learning paradigm, I'm now going to optimize this worst case subpopulation performance. And again, the hyperparameters P and alpha modulate the level of risk aversion, the extent to which you care about minority groups. So alpha was, again, the size of the minority subgroup, minority proportion. So if alpha is big, that means you only care about big enough minority subpopulations. And P was the probabilistic way in which we're measuring the size of these sets. So when P was small, again, we were being less risk averse, less conservative. And as P grows and as alpha goes to 0, we're becoming more risk averse, more conservative. In other words, we're caring more and more about smaller minority groups. Okay. So again, this is the same formulation, the worst case subpopulation performance. And since we only have access to a finite number of samples in practice, I'm just going to take an empirical approximation of this population average. So I'm just going to replace it by an empirical mean. And this is the ultimate optimization problem that you want to solve in practice. And this is a really nice formulation because if you started it out with a convex loss function, then this formulation is jointly convex in theta and eta. So you can apply these nice black box interior point solvers to solve this problem. And even more, you can come up with these efficient first order methods so that you can solve this formulation, this empirical worst case subpopulation performance, even in large scale machine learning applications that are quite common in these modern settings. So computationally, this is a really nice formulation. Now I'm going to study its statistical aspects. So in particular, I'm going to study the extent to which we can optimize these worst case subpopulation performances by only looking at a finite number of data points. So to do this, I'm going to take a particular viewpoint today. So I'm going to consider, so this is what's known as the minimax principle in statistics. So I'm going to consider a statistical modeler, me, who's trying to come up with a procedure theta hat that maps n data points that you observed to a statistical model or a decision that you want to make. And I'm going to consider nature choosing the data generating scheme, P observation. So n data points are going to be drawn from this data generating scheme, P observation. And my procedure, theta hat, that I chose as the modeler, is going to take these data as input and then spit out some statistical model or a decision. Now, an appropriate notion of performance in this setting is to consider the worst case subpopulation performance, so that's what this notation was, suffered under my procedure theta hat, and to compare it with the best thing that you could have ever done in the limit of infinite data, this population optimum. So this term is what's known as an excess risk. And since I don't know what nature is going to choose, I'm going to take this maximum over P observations, the data generating schemes. And then my job as the modeler is to come up with a procedure theta hat that minimizes this excess risk, this notion of performance. So this is a rather fundamental quantity in statistics because it measures the extent to which we can optimize these worst case subpopulation performances by only looking at a finite number of data points, and here denoted by n, the sample size. Now, our main result today shows that this minimax risk scales and goes to 0 at this exact rate of convergence, which is quite interesting and a non-standard rate of convergence. Because when p is less than 2 and you're being less risk averse, when you're only caring about large enough minority groups, you get the usual parametric rates of convergence, the 1 on square root of n central limit theorem type rates. And when p is greater than 2, when you're being risk averse and you're caring about smaller minority groups, you get this slower rate of convergence. And the way we're going to show this result is by taking a two-pronged approach. So first, I'm going to substantiate this guarantee by coming up with a procedure, theta hat, that actually achieves this rate of convergence. And then I'm going to prove a fundamental hardness result that says that no procedure that I could have come up with as the modeler can do better than this rate of convergence. So this in particular gives a lower bound on this minimax risk and concludes this, the proof of this theorem. So first I'm going to substantiate this guarantee. So to do that, I'm going to need some procedure. And I'm going to exactly use the empirical procedure that I had in a couple slides back. So this is just optimizing the empirical version of the worst case subpopulation performance. And I'm going to denote the solution to this optimization problem, theta hat. Okay? So this is a really standard natural procedure, the empirical plug-in procedure. Now what this theorem shows is that with high probability, the worst case subpopulation performance suffered under this empirical plug-in model is comparable to the best thing I could have ever done in the limit of infinite data, the population optimum, up to an error rate that scales like this, which exactly matches what we had in the previous slide. And here, the term, this n of theta, it measures the size of your parameter space. So intuitively speaking, if this parameter space that you're searching over was really big, then maybe finding the right solution, the optimal solution in this space can be quite difficult. So this quantifies this difficulty in this result. Now, the interesting thing about this theorem is that this very standard natural procedure, it achieves this very non-standard rate of convergence. So again, here a phase shift occurred at p equals to 2. And as you grew more risk averse, as p grew to infinity, as you cared more about these minority groups, you suffer this slowdown in your rate of convergence. And this is what makes the proof of this result also quite interesting and somewhat non-standard. And I'd be happy to go into the details offline if any of you are interested. Now, we can actually show that this rate of convergence is, in fact, optimal. And you can't improve it. So that's what this next result shows. So this result shows that there exists some loss function such that the best procedure, theta hat, that I could have come up with as the modeler still has to suffer this error rate. And in particular, this matches what we had in the previous slide. This shows that the standard procedure, the empirical plug-in procedure, is optimal in terms of its sample complexity, sample efficiency. And this fundamental hardness result, it quantifies the underlying statistical price that you have to necessarily pay if you want to optimize these subpopulation performances. And it says that the slower non-parametric rates of convergence is necessary and unavoidable if you want to be risk averse, if you want to care about smaller minority groups. So again, I'd be happy to go into the details of the proof. It's an information theoretic lower bound. I'd be happy to go into the details offline if any of you are interested. So together with this lower bound and the upper bound that we had in the previous slide, we have now quantified the rate at which we can optimize these worst case subpopulation performances by only looking at a finite number of data points. Okay, now I'm going to empirically verify that our approach actually works in a certain sense. So I'm going to present a couple of experiments today. So the first setting that I'm going to talk about will have these underrepresented demographic groups who are significantly disadvantaged. And it will be somewhat unclear a priori who these disadvantaged subgroup is. And we'll see how a worst case subpopulation procedure can automatically identify these disadvantaged subpopulations and improve performance on them. And then as our next experiment, we're going to study a balanced scenario where you have evenly represented demographic groups. So you actually have zero underrepresentation bias. But we'll still see how in this setting there are fundamentally difficult subpopulations that naturally arise. And we'll see how our worst case subpopulation procedure can still learn from these fundamentally hard subpopulations and provide some uniform level of performance across all demographic groups. So as our first experiment, let's go back to the warfarin dosing example. So again, we want to come up with a personalized drug dosage for warfarin, the most commonly used blood thinner in the world. And so given demographic and genetic information, your covariate vector about a patient, you want to predict the patient's therapeutic dosage of warfarin. So today I'm going to use the prediction error, the squared loss, as my notion of performance. And of course, this is not the ultimate clinical outcome of interest. That'll be whether this drug had stopped a heart attack or something like that. But that's very difficult to measure. And this is actually a good proxy of performance because these therapeutic dosages, Y, were found by trial and error on each of these patients by the doctors. It was, in fact, this prediction error that was used as a proxy of performance by the original team of doctors who amassed and analyzed this data set and presented in the New England Journal of Medicine. So today I'm going to just stick to the prediction error again. And as our baseline, I'm going to use the average case procedure. Excuse me. So that's minimizing this expected loss. And since you only have access to a finite number of data points, I'm going to minimize this empirical version. And this is what's known as the empirical risk minimization scheme, ERM, or the sample average approximation scheme in operations research. Since ERM has fewer syllables, I'm just going to stick to ERM today. And in the warfarin dosing example, we wanted to minimize this prediction error, again, the squared loss. Now, recall that the model that was generated from this method had a really poor tail performance. And in particular, for patients who required a high dosage of warfarin, it had a really high prediction error. And we'll see how on this unseen disadvantaged subpopulation, how our worst case subpopulation procedure can provide more reliable personalized treatments. So here I'm plotting the prediction errors incurred on this disadvantaged subpopulation. So that's the y-axis, and the x-axis is the minority proportion alpha. And the ERM procedure, the average case procedure, doesn't depend on our hyperparameter choice alpha. So that's the flat red line. And here we see that depending on your risk preference, your ability to optimize this optimized performance on this disadvantaged subpopulation, it varies somewhat. And in particular, when p is equal to 3, when you're being very risk averse, you can get away with using a really large value of minority proportion alpha, and you're still able to significantly improve performance over ERM. But perhaps more interestingly, when p is equal to 2, we see that you get this set of statistical models that are more robust to your specific hyperparameter choice alpha. And regardless of the value of alpha that you choose, you see this performance improvement. So let's just focus on this particular choice, particular risk aversion level, p equals to 2. So recall that Asians who required a high dosage of warfarin was quite rare, about 1% of the total population. And they suffered a really high prediction error under the average case procedure. Now, as we become more risk averse, as alpha goes to, say, 5%, our procedure, the worst case subpopulation procedure, can automatically identify these particular disadvantaged subpopulations and improve performance on them. And similarly, for blacks who require a high dosage of warfarin. And another interesting thing here is that, so here Asians who required a high dosage was 1%. And if you used alpha equal to 10% in our procedure, then our procedure is only optimizing against very crude granular minority groups. So initially, you don't see any performance improvement on this very particular tail subpopulation. And as you become more risk averse, as alpha becomes 5%, our procedure actually becomes fine-grained enough to do this. But of course, this performance improvement, it's not free, and it comes at a slight deterioration in the average case performance. So there is this trade-off that occurs naturally in this setting. And this is a setting where you're perfectly okay with this trade-off because, again, you don't want to kill people. But in other settings, it may or may not be true. But in these high-stakes domains, I think you're mostly okay with this trade-off.
So you're able to sort of start honing in on the high dose Asian population before your subpopulation percentage gets down to the 1%.
Mm-hmm. Mm-hmm.
Similarly, with the black population, you're able to get there before your. So why?
Good. We don't have a good theoretical explanation of that. So the best answer we have for actually choosing these hyperparameters is essentially cross-correlation on some disadvantaged subpopulation you can imagine, or maybe you have some idea of what the prediction errors are like. Maybe you just look at the tail subpopulations depending on the current model, and maybe you have some sense of what a prediction error equal to 10 or 8.5 means. And maybe you're okay with that, maybe you're not. Okay, Now, as our second experiment, we're going to study a balance scenario. So here we're going to simulate a setting where we are careful about data collection, and we actually have evenly represented demographic groups. So here the task is fine-grained recognition, and we're going to look at dogs instead of humans. So here we want to classify an image of a dog to its dog breed, and there's going to be 120 different dog breeds, 120 different classes. So this is a fairly difficult task even for humans. I can't do this, for example, at all. And here this is going to be an interesting setting because there's going to be no underrepresentation bias. So this means that we're going to have the exact same number of training images per dog breed, per class. Now, even in this balance scenario, if you train an average case ERM procedure, and if you look at the class-wise accuracies, then you can see that there are certain dogs that you excel at classifying, but then certain dogs, these dogs, you do really poorly on. Your error is really close to 100%. And this gap in performance can be as large as 70% in accuracy, which is quite a big gap even because we started out with a setting with no underrepresentation bias. Now let's see what our worst case subpopulation procedure does. So here I'm plotting the variation in these class-wise accuracies over these 120 different dog breeds. And we see that as alpha goes to 0, as your minority proportion becomes smaller, as you become more risk averse, our procedure is able to decrease this variance in a pretty monotonic fashion, which is kind of interesting because our procedure is not controlling for this quantity in any explicit fashion. But by trying to provide a uniform level of performance across all of these different demographic groups, it's sort of doing this. And another way to see this is on this next plot. So here I have 6 different models. The first one is ERM, the average case procedure. And then the rest are our models with varying degrees of the minority proportion. And here we see that, so here I'm plotting, I'm taking the X classes for each of these models that it does the worst on. So I'm taking the worst X classes under each of these models, where X is the value that varies in the horizontal axis. And I'm computing the error rates on these worst X classes. So that's each point in this plot. So the left-hand side of this plot is your tail performance. So this is a fairly non-standard plot, so it takes a while to absorb. If you have any questions about what this actually means.
You may have said it, but I think I missed. It is a guarantee regardless your machine learning models.
Yes, this doesn't depend on the actual model that you have. Thank you. And it actually scales to fairly large deep learning settings as well. So you can actually use really large architectures.
But if you use some models that are not capable of recognizing the data, how can you guarantee?
Good. So here we use a particular kernel feature to do this. So that average case model having this big gap among different dog breeds, you actually see that type of phenomenon across different model classes. So I've ran this on maybe a pre-trained ResNet 50, a really large, big deep net architecture, and fine-tuned on this particular data set or something like that. And that still has the same problems. I've also tried this on CFAR 100, which is a standard data set with 100 different classes, and you also see this type of a phenomenon. So I think it really is a matter of the underlying procedure, not the features or the models itself. Thank you, that's a good point. Yes, good. Okay, so here I'm taking these 6 models, and I'm taking the X classes for each of these models that it does the worst on. And then on these worst X classes, I'm computing the error rates, and that's each point. So here I'm taking the 40 classes under each of these models that suffer the worst, and I'm computing the error rates on these 40 classes. So this is the worst case performance. This is the average case performance. Very good, I think.
So this is very interesting. So what I'm thinking, what I originally thought when you started explaining the problem, why not just oversample? That's folklore.
Good. Good.
Oversample, underrepresentation, so that your objective function. What you're saying here is, no, that even is not sufficient.
So if you oversample proportional to your loss, then this is that type of procedure. If you imagine solving our population worst case population problem using some online method based on maybe a subsampled and oversampled SGD type procedure. So you're able to show that. Are you able to get how much you have to oversample? Good.
equivalent to this?
Good. So we essentially view this as an optimization problem. So we do come up with some first-order methods for solving this, which depends on coming up with how much to oversample. So this, you can actually show that these worst-case subpopulation performances is actually exactly some distribution robust optimization problem. So there's the equivalence. I actually have a slide on that. I'd be happy to show that at the end of the talk. Thank you.
If your model tends to overfit the data, do you see
Good. So this is on top of any regularization scheme that you'd imagine using. So you do your usual cross-file for L2, L1, lasso-rich, lasting nets.
Overfitting, would you face a problem because the subpopulation is much smaller? So
Good. Yes. So that's what the theory said as well. So if you want to really care about smaller minority groups, there's like a fundamental hardness. There is a fundamental hardness there. So at the very least, what I'm advocating for here is at least plotting, not even optimizing, just plotting these worst case subpopulation performances, or just looking at the worst set of people when you train your deep net on TensorFlow or whatever framework that you use, and just have a sense of how many people you're killing basically. So again, sorry, just to explain what goes on here. The blue model is the average case procedure, and as you become more risk averse, we see that your tail performance improves drastically by up to 20% in accuracy, which is a really big gap considering that we're using the exact same features. And thereby, we're actually able to provide a uniform level of performance across all of these demographic groups, and we actually improve performance across all different demographic groups, which is kind of interesting here because there's actually a regularization effect. So I actually have a line of works that also explain this effect in a number of other papers, and I'd be happy to explain this offline.
So those curves don't monotonically improve with alpha 7?
Good, yes. So I think there is definitely this overfitting effect, and that's what you see here. You're being too conservative. Thank you. Okay, all right, let me briefly summarize and then briefly talk about my broader research in this. So far I talked about how an average case procedure, the standard machine learning paradigm, yields models that have really poor tail subpopulation performance, and wanted to leverage this risk aversion idea. So I made this explicit connection between worst case subpopulation performances and risk aversion. And we leverage this idea in large-scale machine learning scenarios. I've also done a number of other works in this domain, and I'd be happy to go into the details if any of you are curious. Now, since I'm almost out of time, let me use that time to discuss and do a brief overview of my broader research agendas. So in general, I'm quite interested in the interplay between large-scale machine learning methods and decision-making problems, again, that arise naturally out of operations research or other engineering domains. And so I think that this could be maybe applying some of these large-scale prediction models to a downstream decisions task. So I think this is a direction that many people in this big community are now beginning to talk about. But I think that this relationship can also go both ways. And I think there's a really nice set of ideas in the communities that traditionally studied these decision-making scenarios, for example, operations research. And I believe that if we can scale these ideas up in a nice way, I believe that these ideas can help us tackle some of these fundamental challenges that we're currently facing in statistics and machine learning right now. So as a theme, I've been building these robust and reliable machine learning algorithms that can provide some level of guaranteed performance when they're deployed. So as we approach this age where these machine learning algorithms are now being applied to high-stakes domains throughout medicine and autonomous driving and so on, I believe that these reliability concerns will become increasingly important. So I've worked on a few directions under this broad umbrella, and I'd like to go over them briefly now. So far I talked about how we can learn statistical models that have uniform performance across minority subpopulations. So subpopulations is a particular distributional shift that you want to maintain reliable performance over. And in practice, there could be other shifts that may naturally occur. So for example, in computer vision, you may want to train an object recognition model to be deployed on, say, a self-driving car, and maybe you have data collected over a Californian highway. But under operation, your car will go to places that doesn't look like a Californian highway, maybe crowded cities like Chicago. So I've been interested in developing statistical procedures that can maintain a level of performance over these different sets of environments. And so far, I've explored procedures that are agnostic to these specific target environments during the training process. So this is actually a data set that we use to demonstrate our method. And more recently, I've been interested in, and I've been working on observational studies and causal inference, which is a setting where you don't have any control over how your subject gets assigned to either the treatment group or the control group. So this setting is quite ubiquitous throughout population health and economics. And in these types of scenarios, you almost always have these unmeasured variables that affect your probability of treatment. So for example, if you're a researcher studying the question, does excessive drinking cause lung cancer? And if smoking is correlated with alcohol consumption, and if you didn't get to observe whether people smoked or not, for example, then this will likely confound your fundamental causal understanding of this phenomenon. So I've been developing statistical procedures that can maintain a level of performance even under the presence of a certain level of confounding variables. And I believe that in general, these types of uniform performance guarantees are quite crucial to getting at reliable machine learning procedures. And I think there's a lot of interesting problems in this broad direction here. Another big direction I've been working on is developing machine learning algorithms that are provably robust. So recently, many people have observed that these deep neural networks are extremely brittle to even small amounts of noise. And you can basically come up with these imperceptible perturbations to inputs so that, for example, an image still looks like this exact same image to humans, but the model now thinks it's something completely different. So here we have a 3D printed turtle, which the model classifies as a turtle initially. But if you add in a few red dots, it still looks like a turtle to us humans, but the model now thinks it's a salt rifle from every angle. And this is fairly scary, considering the fact that you can then use similar techniques to fool self-driving cars into thinking that stop signs are basketballs. So here we have two stop signs, and the one on the right has been tainted with this type of a noise, and the model now thinks it's a sports ball. And it can't even figure out where to put the bounding boxes to figure out where the stop sign is. So I've been developing principled procedures that can learn to provably defend against these small perturbations in the underlying input. So I've been leveraging techniques and ideas from the robust optimization literature. And I've been making connections between classical statistics like empirical likelihood theory, as well as novel regularization schemes that allow you to generalize better to the test set, even in high dimensional scenarios where you have over-parameterized models and high dimensional features. Now, these couple directions were mostly about how we can learn models that either perform uniformly well or are provably robust. Now, most recently, I've been very excited about safety testing procedures. So this is a slightly different perspective in that you think of a large, complex system as given, and you now want to certify its safety. So in performance-critical applications like autonomous driving, it's imperative that we have a rigorous validation framework. But the prototypes that are actually operating on real roads right now, they have a number of failure modes that are quite poorly understood. And some of them have even been caught on camera. So here we have a Mobileye vehicle that's casually running a red light. And on the right, we have Tesla Autopilot that's being involved in this very tragic, fatal accident. So these accidents, they underscore a need for some notion of a driver's license for these autonomous vehicles. But as we saw in these videos, real-world testing of these vehicles is prohibitively expensive because it puts the public at risk. And due to the rarity of these accidents, they're going to have to drive billions of miles before they can collect enough data to be able to statistically certify their safety. Simulation-based testing frameworks for these high performance critical systems. So for example, in the autonomous driving setting, I've built up a photorealistic simulator equipped with a realistic model of human driving. And because these accidents are rare, I've been leveraging techniques from the rare event simulation literature to accelerate the evaluation of these probability of rare accidents. So in particular here, we have a video of an accident that was generated by our simulation framework. And I've also been building similar simulation-based testing systems for an artificial pancreas for type 1 diabetics, which is a medical device that monitors your blood glucose levels and injects insulin to control it. So here the problem is that the existing products on the market, they don't tailor to the individual's insulin sensitivities. So people have been making these ad hoc modifications to their devices, essentially hacking into their FDA-approved devices. So we're hoping that our simulation framework can help certify and verify the safety of these in individualized settings, because we're not going to be able to run a clinical trial for each of these personalized scenarios. So this has mostly been an applied direction of mine so far, where I've put in a fair amount of engineering effort. And going forward, I'm also very interested in it from a theoretical and methods perspective as well. Because a lot of these rare event simulation techniques, they don't scale to nowhere near the high dimensional problems that we actually want to solve in practice. So I think it'll be quite impactful if we can build more scalable versions of these algorithms. So in all of these directions, I think there's a lot of interesting problems to be worked on, both theoretically and empirically. And going forward, I'm also quite interested in the interplays between all of these directions and the actual decisions that you have to make in downstream operational tasks. So I believe that by actually explicitly modeling these decision layers, we can better leverage the potential of these large-scale prediction models and decision-making scenarios. I think I'm out of time, so I'll end here. Thanks a lot for your attention, and happy to answer any questions.